In the next section, 8.2, the conic that we will be studying is the ellipse. So to start with, I want to give you the mathematical definition for ellipse, and then we'll at least take a picture, try to get a picture, take a look at what an ellipse looks like, and see if we can label some pieces and parts. So, an ellipse is known as the set of all points in a plane whose distances from two fixed points have a constant sum. The fixed points are called the foci, which is the plural of focus. So we are going to have basically two focuses, or foci, in an ellipse, as opposed to the parabola that just had one focus. The line through the foci is called the focal axis. The point on the focal axis midway between the foci is our center, and the points where the ellipse intersects its axis are our vertices. It's a mouthful, so take your time, take a second, get that written down. If you're still writing, you obviously want to pause this because I'm going to move to a picture real quick and see if we can get an idea of what this means. So you won't want to really watch this until you're ready. But I'm going to really focus on the fact that I think we all can envision an ellipse, and our oval shape. Where will the foci be? And the fact that the ellipse is all points whose distances from these two fixed points have a constant sum. So I really want to show you what that looks like. So here's our oval-shaped ellipse. F and G are the foci, and so their distances are represented with the blue line and the red line. You can see the blue line and the red line here are basically being added together. So the sum of the blue and the red line should be the same for every point on the ellipse. So watch as I drag this point P and move it anywhere on the ellipse. Now, the blue line and the red line obviously change. They're not the same, but their sum is always constant. It's staying on this sum line. We don't ever go off of it. So even as red gets bigger and as red and blue change from getting big to small, the FG itself, this length in total, doesn't ever change. I think I can even change, so as my foci changes, obviously my ellipse changes as I move the foci. This is always cool to look at, is when the two foci are at the same point, you actually have made a circle. So again, it's just kind of fun to pull some of that stuff around. Okay, back to our notes. There was a lot of vocab in this particular section, so I just want to make sure we have everything straight. Center, I think, is pretty easy. Now the foci are going to be inside here, a specific distance away from the center. We call this distance from the center to the foci, we call that our C value. Oops. We'll come back and label that in just a few minutes. I'm going to keep going here. So there's our foci. Our vertices were where the ellipse meets the focal axis, which is what they called the axis running through our foci. So the focal axis in this case is the x-axis. A semi-major axis, that's half of your focal axis. So the semi-major axis would basically be from this vertice to the center, or from this center to this vertice. That would be the semi-major axis, and then the semi-minor axis would be half of our other axis. So it would be, this is our minor axis, so the semi-minor would be from the center out to this particular endpoint. Now we can label the same pieces and parts over here. I've just flipped the major axis or our focal axis on this one. So this longer piece, the foci would be on this axis this time. So that makes the y-axis our focal axis. Now our vertices are here and here. And then the center is still 0, 0. Semi-major would be half of the focal, semi-minor, half of the minor. Standard form, we've actually looked at this for an ellipse already. So our standard form is x squared over some number squared, y squared over another number squared equals 1. Now our a and b are going to have some importance here. A is the length from the center to each vertice on the major axis. So because this is the major axis, our a squared is always bigger. And the variable that it is under basically tells you what axis you're going out on. So since our a squared is under the x squared in this problem, I would be going out on the x-axis. So your focal axis is the x-axis. The center is at 0, 0 for this problem because there's nothing else with our x squared or our y squared. Now this time, because the a squared's under the y squared, that makes our focal axis the y-axis, and our center is at 0, 0. Let's real quickly look at the equation when the center is not at 0, 0. So you have a minus h quantity squared, a minus k quantity squared on your x's and y's. Your center will be at hk, hk, and you still have to be careful about what variable the a is under. In this case, the a is under the x-axis, but we're not just on the x-axis. We've actually moved over h units, or to the right or left, depending. So let's pretend h is 2. So I'll have gone over 2. Let's pretend k is 4. So we have a go up 4. This is our center. And because the bigger number was under the x, when I go to make my foci, when I go to make my vertices, I'm going left and right. So this is your focal axis. So the focal axis is going to be, while you're on the x, you're going through the y value. So the focal axis is at y equals k. Now the opposite will be true over here. Let's say I keep the same points. Let's say I have a minus 4 here, and say I have a minus 2 here. The center is still at hk, so I'm going to go over 2 and up 4 for my center. But when I go to label my vertices, I'm going to go on the y-axis, my a units. This is going to be my focal axis. So the focal axis is an x equals h scenario here. So again, just like with parabolas, if you can picture the graph and picture what's happening, I think that's going to be really important. Now, the A helps us get each vertice on the major axis. The B helps us get the distance in the other direction on our minor axis. So just with the A and the B, you can draw your ellipse. What you might notice, though, is that how do we figure out where the foci are? There wasn't anything in the equation itself that tells us about the foci. And that's where we want to do some labeling back on this picture. And I'm actually going to do it on this one. So we know the distance from the center to each vertice is A. Then we also know the distance from our center out to this endpoint is B. And C is actually the distance from the center to a focus point. So this is our C. This is our B. Now you might see a right triangle forming. And what's interesting is this hypotenuse hypotenuse. This diagonal length from the top here to the focus is actually A. So the special relationship between A, B, and C, to help you understand how these distances connect to each other, is B squared plus C squared is equal to our A squared. It is a Pythagorean relationship, but it is backwards and a little different than the Pythagorean relationship you are used to. So it's really important that you get down this relationship between our A, B, and C lengths, because that is definitely going to help you when graphing. If I ask you to label your focus, you're going to need to know what the C value is. The equation will give you A and B, but you will have to use this relationship to find C. So if you actually solve this backwards for C, we know C squared is equal to A squared minus B squared. So different from our typical Pythagorean relationship. We could show the same thing over here and we would get the same idea. I just wanted to at least give you a picture of that.